Today we're going to talk about plate tectonics. Plate tectonics because that's next. Plate tectonics first began in history as Continental Drift proposed by a man named Alfred Wegener. He was a pretty cool dude, banker. You can kind of picture him sitting behind his desk. He's got a big old map on the wall, and he says, "Hey, check that out. That looks like the continents used to fit." And he begins his hobby of figuring this out. Could it be possible? Is it true? Is it real? And so his idea was that the continents used to be one large landmass called Pangea, and the idea that they aren't anymore was continental drift. So in his research, he comes up with 4 pieces of evidence. Number 1 was the jigsaw puzzle. It looks like the shapes of the continents fit. Number 2 is fossil evidence, which is matching fossils on opposite continents. When you put those together, they start to look like they match. And so this example here is of Mesosaurus. Mesosaurus is about a cat-sized freshwater dinosaur, so it would have lived in like lakes and streams and fresh water. But if you look at the fossils, they match across this big wide ocean. Now it's problematic for several reasons. Number 1, it's so small. Number 2, saltwater organisms have special glands and whatnot to get rid of the excess salt, and Mesosaurus wouldn't have had one of those. And so could it have swam all that way? Not likely. It's too small, and there doesn't have any way of getting rid of all that salt, so it would have, dehydrated itself. So there's really no way for that to have occurred on 2 opposite continents that just so happen to match at the same time. So that was probably one continent. That was then backed also by geologic features. If you line up mountain ranges and ages and the kinds of rocks along edges of continents match too. So another example is diamonds. Diamonds have to form in very high heat and pressure, and so those diamonds then are also found in matching areas along coasts. And so, that becomes, how much of a coincidence are you looking for before you start to go, yeah, that used to be one spot. And then last one, ancient climates. Glaciers leave these scratch marks in the bedrock. They drag these big boulders along the bedrock, sort of like you dragging your fingers through the sand, you'd leave a pattern. Well, the boulders leave a pattern along the bedrock, and those glacial markings match along separate continents in terms of the direction, the depth, everything. And those also can be found in places that are now tropical, so we can start to look at, hey, those probably used to be one continent. Well, there's a problem, though. Wegener didn't have a driving force. He kind of thought these continents kind of tiptoed through the oceans. They waited in between, and they just sort of moved. He wasn't sure why. And so the scientific community was like, psh, you don't know what you're talking about. You're a banker. And so they ignored his theory for about 25 years. Then, again, as we were starting to learn more about the world we live in, along comes Marie Tharp. And Marie Tharp, back in the 50s, women were still not valued in the scientific community, and she starts analyzing some data that's coming in from some male researchers, and she says, I'm starting to see this pattern, that there's this feature that's running along the bottom of the ocean floor, and it matches the coastline, and man, maybe the ocean floor moves with these continents. And so she came up with the idea of plate tectonics, that lithosphere is broken into these big plates and includes the ocean floor. So that resolved kind of one of those problems of continental drift, that the ocean floor was included in the movement. And so the lithospheric plates then ride on the asthenosphere. Well, the other part that they had was that there was convection currents, that whole idea that hot stuff and cold stuff, you got it. Hot stuff rises, cold stuff sinks. And so convection currents are that. And you can ask your friends about the demo we did in the density tank with the hot water pushing the wooden blocks along. I'll see if I can't get that posted maybe later. So the idea that this hot mantle rock near the core heats up, it rises, and you would get some sort of spreading incident here. Then as it kind of is out on this outer edge, it cools and it starts to sink back down, and the sinking pulls the lithosphere down as well as it getting pushed from this side. So you get this convection current that moves stuff because hot stuff rises and cold stuff sinks. So again, that mantle is a liquid, and that temperature of the Earth is warmer as we get near the center. So that mantle rock near the center is going to heat up and rise. Those molecules are going to spread out and move more, and then it's going to push along that plate above, and then it'll cool off and sink back down. And so it's sort of like a grocery store conveyor belt. So think about like when you put your groceries on that belt and it kind of slides it towards the cashier, it moves it down towards the bagging area. Yeah, we're the groceries. So that is what that is all about. Fun stuff happens when the plates move. So here you can see a road that has had some issues after an earthquake. And this is one of my favorite pictures, this one here on the right. So take a second, pause the video, and see if you can notice anything funny and what it is. And hopefully what you notice are, these nice long rows or one continuous line until right here where the dude is standing. And you can see that they're kind of offset a little. This might have gone here, it might have gone here, not really sure. It looks like it goes off to the right. And what you notice is, they no longer match. It's no longer one continuous line anymore. And it's not like the farmer, was going along and then picked up his equipment and shoved it over, 2 foot and then kept going. That used to be one continuous row right here. And what happened was some event either shifted this to the right or shifted this foreground part to the left, and you get this offset rows. And so fun stuff happens. Here we have a picture of the 1906 San Francisco earthquake. We learned a lot about building codes because when buildings collapse, gas lines break, and when gas lines break, fires happen. But when gas lines break, so do water lines. And so we have to, in California, there's building codes now that help prevent that from happening. Volcanoes, this is Mount St. Helens in 1980, erupted, pyroclastic flow that took out quite a bit of stuff. And then things like mountains and islands. So our Aleutian Islands in Alaska, that little tail of Alaska, those are caused by plate tectonic movement. And then here you can see Mount Rainier in the background, where we have some other tectonic plate here activity here in America. There's 3 different types of plate boundaries where you need to be aware of. Convergent and divergent hopefully are fairly easy for you. You remember these from meteorology. And so transform is really the next new one, and that's a place where 2 plates slide past each other. So here's kind of a map that we're going to be looking at. Please keep in mind that this is very, very sanitized. It looks really clean and tidy and neat, but the world is much messier than this. These lines would all look like zippers. So you can picture this is the center of your hoodie, and then you have the little zipper teeth that zigzagged back and forth. And then each of those lines picture a zipper on as well. So it's a much fuzzier joining of these plates than what is pictured here. So the first one we're going to talk about are transform boundaries, and transform are the slide past ones. It's not a smooth movement, it's a slip and stick pattern. So if you take your hands and put them together, make it 2 fists and then put your knuckles together and try to slide those knuckles up and down, that's kind of what it would be. Slip a little bit and then stick, and so you get lots of earthquakes. The other thing to keep in mind is in a transform plate boundary, we tend to think of, like when you do the knuckle thing, you're moving one hand up and one hand down, or one hand forward and one hand back. But it's not necessarily just that. It is also like passing a car on the highway. So you can be in the fast lane and another car can be on a slow lane. You're both going the same direction, but you pass the other car. That is what is going on. That is what's going on here along North America. We have this transform boundary kind of in the California region. The North American plate's only moving north a little bit. It's mostly moving west. And the Pacific plate is moving both north and west. So the Pacific plate has a tendency to move much faster than the North American plate. What does that mean? It means California is not going to fall off. It's just going to slide north. And so the Pacific plate is passing the North American plate on their journeys north. Excuse me. The next one, we're going to talk about our divergent plate boundaries, plates where the plates are moving away from each other. And so this is a place where new crust is formed. You actually make brand new baby crust at these places. On land, we call these rift valleys, and in water, we call it mid-ocean ridges. This is what you did your lab on. And so on land, it's called a rift valley, and they usually fill with water. So we see these there's one in Africa, and there's also at the Red Sea, are good examples of those. Underwater, they form actually underwater mountain ranges that are much bigger than any mountains we have here on Earth, because they have this rift or this tear in the center, and it allows the magma to flow to the surface. So in other words, you get a bigger tear down into the surface of the Earth. This makes new crust be in the middle because new igneous rock is being formed right there. And the new crust, as it forms, it forces the older crust outward and away. And so you get lots of earthquakes, and you get lots of earthquakes, lots of volcanoes here. Not sure why my animation's not playing. This guy is usually going outward. And so if you pull this up on your PowerPoint on Blackboard, you'll notice that this is all moving outwards as this new rock bubbles up. It pushes that out and away. So these mountain ranges are very tall, and then that moves outward. And now that's not the only way we know that that these happen. We also know that Earth's magnetic field happens, and so if we look at the magnetism of those rocks around that mid-ocean ridge, we see these symmetrical bands along those rift valleys that alternate north and south directions, but they're on both sides are always the same. And so you notice that hopefully that same pattern in your data, that you had symmetrical bands of that as well. Now that doesn't just happen with the magnetism though. You also can see that in the age of rocks. You see that older rock is farther away from the rift valley than newer rock. Newer rock is in the middle, and that's symmetrical in terms of the ages of those rocks. And we can also see fossils. The fossils will also be symmetrical. So fossils from recent eras end up closer to that rift or that valley, and then fossils from older areas are farther away. And then finally, we have convergent boundaries. So the most recent earthquake in Nepal, this happened at a convergent boundary, actually happened here in this general area to the right of these red arrows. But convergent boundaries are a place where two plates move toward each other. It's the place where crust is destroyed and recycled. So if we only had divergent boundaries, the Earth would be getting bigger and bigger. But the Earth is not, because we also have these convergent boundaries. And so it's destroyed in one of two ways, essentially. If we crash two continents together, we get a mountain, and the crust is destroyed because it's turned back into sediment that then is carried away and moved elsewhere. If it's a continent crashing with an ocean, you get a subduction zone, and that crust is recycled because it's melted down and goes into that volcano. And then ocean plus ocean gives us an island arc. And ocean plus ocean is the same essentially as that continent plus ocean. The only difference is it happens farther off in the ocean, and so when a volcano pokes its head up out of the sea, you get an island. And so this would be like the Aleutian Islands in Alaska. So Alaska is that kind of island arc, okay? And Japan as well is one of those. So all these islands along in here are also those same kind of islands. So continent plus ocean gives us a subduction zone, and this is because the continental crust, reminder from last week, is thicker and fluffier. It's less dense, and so it kind of floats. And the oceanic crust is thinner and denser, and so it gets pushed underneath the continental crust, which then is hotter, and so it melts, and then when it melts, it bubbles up, and we get a volcano. So the Andes Mountains of South America are another example of that. So here are some pictures. So what we see here is that oceanic crust is getting forced down underneath this continental crust. So this oceanic crust is this thin yellow line, and then the continental crust is this big, thick, kind of olive color. And so this gets pushed down, melted, and makes these volcanoes. So Mount St. Helens, Mount Rainier are this kind. We do have a tiny little bit of a convergent plate boundary up there in the Pacific Northwest. Oceanic plus oceanic. Here you see two smaller, thinner oceanic layers, and so it's the same type of dive down and bubble up that we see, but now it bubbles up off the coast, and so it picks up its name island arc. And so this would be like the islands in Alaska, or Japan would also be this type. And then this was what happened in Nepal this last week. So here we see two continents crashing together, and so Mount Everest is made in this way, and the Andes Mountains are made in this way, where the two continental crusts push together and there's really no way to go but up, and so up they go. And so Mount Everest, its current height is here, and it grows by about 2 to 4 centimeters every year. And so there's a picture of Mount Everest's peak. It was on base camp where those hikers survived an avalanche. You can picture an avalanche going down one direction and kind of out. And as it goes out, it sends out less stuff. And so they were kind of on one of the outs areas, and those hikers that had the video made it into their tent and were able to survive. So that kind of is a little bit of insight into that Nepal earthquake. Okay, so those are your 3 types of boundaries. Good luck.